To yet another Hello friends, and welcome to yet another lecture on chemical engineering thermodynamics. This is Professor Arvind Prasad. Today we'll do something interesting. We will look into a problem on first law of thermodynamics. Well, let's have a look at the problem. The problem is air at 420 Kelvin and 600 kilopascal has a volume of 2 meter cube. It is heated at constant pressure until the volume is 6 meter cube. Find the change in internal energy and enthalpy. What is the work done by the gas and the heat supplied to the gas? Now, as you are aware, air for this problem can be treated as an ideal gas. For ideal gas, we know that PV is equal to nRT. Now, we do not need to calculate N, but nevertheless, let's do it. So we'll can then in that case calculate the total energy instead of the energy per unit mole. So let's do that. Now N is equal to PV upon RT. Here R is 8.314 kilojoule per kmol Kelvin. So we get the value of N as 600 kilopascals into 2 meter cube 8.314 into 420 Kelvin. So that's 600 kilopascals into 2 meter cube. That's so much divided by 8.314 divided by 420. So that's 0.3436 kilomole. So that's 0.3436 kilomoles of a gas. Now it is heated at constant pressure until the volume is 6 meter cube. Now for a constant pressure process, we can write P1 V1 upon T1 is equal to P2 V2 over T2. Since P1 is equal to P2, it's a constant pressure process. Therefore, we have V1 over V2 is equal to T1 over T2. Therefore, we have T2 as T1 into V2 over V1, and that makes it 420 into 6 divided by 2. So that is 1260 Kelvin. That's a pretty high temperature. Still, let's go ahead with the problem. Now, the change in internal energy, since it's an ideal gas, we can assume for an ideal gas, Cp is equal to 29.09 kilojoule per kmol Kelvin, and Cv is equal to 20.785 kilojoule per kmol Kelvin. Therefore, delta U for the gas, that is change in internal energy for the gas, is going to be 0.3436 kilomole of a gas into the CV for the gas, that is 20.785 into the change in temperature. That's going to be 1260 minus 420. So the delta U is equal to, let's calculate, 0.3436 into 20.785 into bracket start 1260 minus 420. So that is 5999.04 kilojoules. Now delta H for this process is 29.09 into, that is the Cp. So let's write it in a proper form. So first we get the n 0.3436 into 29.09 into 1260 minus 420. Therefore, this is equal to 0.3436 into 29.09 into 1260 minus 420. That makes it delta H is equal to 8396.07 kilojoules. So we have the two answers. Now we need to find out the heat given and the work done. Now, if we apply the first law to this process, we get delta U is equal to Q plus W. And since it's a constant volume process, we have Q is equal to delta H. Therefore, substituting, we get 5999.04 is equal to 8396.07 plus W. So the work done is equal to 5999.04 minus 8396.07. This makes it minus 2397.03 kilojoules. Now this is the work done by the gas. Now as you can see here, the volume is expanding. So work is done by the gas and we get it as a negative quantity. Since this is a constant pressure process, as we have already mentioned earlier in the problem, the heat given is equal to the change in enthalpy. So the heat given is 8396 0.07 kilojoule. So that was all, my friends. Hope this problem was an very illustrative one, and it helps you in understanding what is a constant pressure process and how do we do the calculations for delta U, delta H, heat and work for a constant pressure process. Keep watching for more videos.